All right, thank you for having me here. It's a genuine honor to be here in a place where the heuristic of generosity really has developed and become an important part of the way that I think and the way that I approach a lot of the problems in technology that we're encountering here. And I'm also very grateful that to be here in a space that's talking about the intersection of science and technology, as well as philosophy and theology as well. My role today is to kind of deepen a little bit what Matthew Harvey Sanders covered, to give you more of the technical substrate, kind of the mechanical reality of what these systems are and what they do, so that when you bring your considerable philosophical and theological resources to bear, you're working with the actual thing rather than a metaphor for the thing. This conference asks two questions. What kind of tool is AI, and can AI be used to help us grow in virtue? I will try to give you what you need to answer both, though I will mostly resist the temptation to answer them myself. A word about method. Throughout this talk, as a technologist, I will use terms like learning, attention, understanding, reasoning as technical terms of art. Their relationship to the concepts you know by those names is precisely what is at issue. Where I use them without qualification, I am reporting how the field uses them. Of course, the philosophical evaluation is ours to make. I will also, at certain points, use vocabulary drawn from Lonergan's cognitional theory. Not to make philosophical claims on his behalf, but because his framework provides the most precise natural language vocabulary I know for articulating what these systems do and do not do. When I speak of insight, things, and judgment, I am offering his categories as instruments of description, whether they apply analogically, univocally, equivocally, or not at all, again, is ours to determine. Now, much of what I will be covering here, Matthew also covered, and part of this repetition is intentional. Because we find that Matthew and I and many of the technologists in our field find that the philosophers and theologians who have strong things to say about the technologies that we're building come from their own disciplines and often misunderstand ours or do not have the technical depth to really work with us in some of the more complicated issues that we're working on as we're building these technologies. So a bit of a return to some of what Matthew talked about, but also a deepening and a view of where, as of a month and 2 months ago, the bleeding edge of the technology is in terms of building these systems and how it relates to how we might think about humans operating. So let me begin with the fact that, of course, as we know, a large language model is in its entirety a single mathematical function. It takes numbers in and puts numbers out. Everything else, the apparent conversation, the seeming comprehension, the occasional flash of what looks like wit, is the consequence of the extraordinary complexity of that function and the extraordinary scale of the data used to define it. The function is defined by its parameters, learned numerical values, hundreds of billions of them, organized into mathematical matrices. A matrix is a grid of numbers that operates as a transformation. It takes a vector, which is an ordered list of numbers, and maps it to another vector. The entire model is a composition of such transformations, matrices multiplied by vectors, passed through nonlinear functions, multiplied by more matrices thousands of times in sequence. Claude, the model built by Anthropic, for example, has parameters in this range. GPT-4, which is 2 models ago now, built by OpenAI, likewise has similar. These numbers were not hand set by engineers. They were learned through a process I will describe from trillions of words of human text. The input to the function is a sequence of tokens, fragments of text, roughly corresponding to words or pieces of words. Each token is assigned a numerical index and looked up in a learned embedding table, a matrix where each row is a vector of 4,000 to 12,000 numbers. This vector is the token's initial representation, its location in a high-dimensional space. The dimensionality matters. In a space of 4,000 dimensions, you have 4,000 independent axes on which tokens can differ. The capacity of such a space is, for practical purposes, unbounded. You can pack billions of nearly orthogonal vectors into it without interference, because in high dimensions, randomly chosen vectors are almost always nearly perpendicular to each other. This is the mathematical fact that makes this whole endeavor possible. The output of the function is a probability distribution over the vocabulary. For each of the roughly 100,000 possible next tokens, a number representing how likely the model judges that token to come next. The model samples 1, the selection governed by a temperature parameter that controls how much randomness to inject, appends it to the sequence, and repeats. Every word Claude writes is generated in this way, one token at a time, left to right, with no revision or planning of what comes later at each time the token is chosen. This is worth sitting with for a moment. There's no homunculus inside the machine deliberating about what to say. There's a mathematical function applied iteratively, producing sequences of tokens whose statistical properties match the statistical properties of coherent, intelligent text. The training process is conceptually simple and staggeringly large. And I think we in tech kind of try to push the largeness of this to account for the remarkable emergent probabilities that these models have when we actually use them. We're trying to articulate that it's, yes, it is statistics, but it's statistics in a way that most of us can't even contemplate statistics. Where if I give all of my writing pre-AI to the tool, it can write like I do. And that kind of changes one's understanding of statistics, at least as a discipline. So pre-training, as Matthew talked about as well, works by next token prediction. The model is shown a sequence of tokens, the opening paragraphs of an encyclopedia article, for example, and asked what comes next. It produces a probability distribution over the vocabulary. The correct next token, the one that actually occurred in the training text, has some probability assigned to it. The loss for that prediction is the negative logarithm of that probability. High loss if the model assigned low probability to the correct answer. Low loss if it assigned high probability. The total loss across a batch of training examples is the single number that the entire training process seeks to minimize. The minimization is performed by gradient descent. The gradient is a vector of partial derivatives, one for each parameter, that point in the direction of steepest increase of the loss function. The algorithm then moves in the opposite direction, adjusting each parameter by a small amount proportional to its contribution to the error. This requires computing for each of the hundreds of billions of parameters how much a small change in that parameter would affect the final loss. The computation is done by backpropagation, a systematic application of the chain rule of calculus, working backward through every operation in the model to attribute credit and blame for each error to the parameter. This loss landscape is the surface defined by all possible parameter settings, with the height at each point equal to the loss. This landscape exists in a space of hundreds of billions of dimensions and has a topology of extraordinary complexity: saddle points, ridges, narrow ravines, broad plateaus, and many local minima. Training does not find the global minimum, the single best setting. It finds regions of the landscape that are good enough, low-loss basins that generalize well to data the model has never seen. Modern research suggests that in very high dimensions, most local minima are approximately equally good, and that the difficulty of training lies not in local minima, but in saddle points and plateaus where the gradient is near zero. The profundity of the prediction objective becomes clear when you consider what successful prediction requires. To predict the next word in a passage about quantum mechanics, you must, in some functional sense, model quantum mechanics. To predict dialogue in a novel, you must model human psychology. To predict a proof, you must model mathematical reasoning. Because human text is about everything, learning to predict it well requires building internal representations of everything human language describes. There's something called the compression hypothesis. To predict is to compress, and to compress is to model. The model is not memorizing text, that would require far more parameters than it has. It is learning the structure that generates the text, the regularities, the patterns, the causal and logical relations that make human language predictable. Each reduction in loss corresponds to the encoding of some additional regularity in the training data. I want to mark this point for you because the nature of that regularity matters. The training corpus is composed of text produced by human beings who have already understood the world, who already had insights. The physics textbook encodes the physicist's insight. The legal brief encodes the jurist's grasp of principle. The novel encodes the novelist's understanding of jealousy or grief. What the model extracts through gradient descent are statistical associations among the products of human insights, among formulations, not among acts of understanding. Whether this extraction constitutes something different than a mere statistical representation in any sort of meaningful sense is something we should probably think about in this room. The model that emerges from pre-training is not yet a conversational assistant. It is a text completion engine, superb at continuing any kind of text, but not specifically oriented towards it being helpful or truthful. Turning it into a useful assistant requires a second phase. Alignment uses several techniques. In supervised fine-tuning, the model is trained on examples of ideal conversations, human questions paired with expert-crafted responses. In reinforcement learning from human feedback, RLHF, human raters compare pairs of model outputs and indicate which is better. These preference judgments then train a separate reward model, a neural network that predicts which of two outputs a human would prefer, and the language model is further trained by a gradient descent to maximize the reward model's score. The reward model is, in effect, a differentiable approximation of human judgment, and the language model learns to optimize for it. Anthropic's constitutional AI extends this with explicit written principles, a constitution that the model uses to critique and revise its own outputs. Rather than relying entirely on human raters, the model generates a response, evaluates it against a written principle. Is this response helpful or harmful? It generates a revised response and trains on the revision. The principles are articulable and auditable in a way that statistical preference aggregation is not. I flag the alignment process because this is directly relevant to our second conference question. The attempt to make a model behave well is, in a precise technical sense, the attempt to encode values in a mathematical system. Whether this achieves something that deserves to be called moral formation or merely behavioral conditioning is a question with deep Aristotelian roots that I will leave to you and to our Q&A. The specific mathematical structure that makes modern AI possible is the transformer, introduced in 2017 in a groundbreaking paper titled "Attention is All You Need." Every frontier model, Claude, GPT-4, Gemini, DeepSeek, Llama, is built on this architecture. In fact, it's why we're in this room having this conversation today, is because of that paper. The transformer's central mechanism is called attention, and the name is both apt and misleading. And here's what it does precisely. Each token enters the model as a vector, its embedding. Call the full set of token vectors the residual stream, the river of information that flows through the model, one vector per token position. Every operation the model performs reads from this stream and writes back to it. The residual stream is the model's working memory. At each attention layer, and this is going to get complicated, but stay with me, every token's vector is projected through three separate learned matrices, producing three new vectors: a query, Q, a key, K, and a value, V. The query encodes what information this token is looking for. The key encodes what information this token has to offer. The value encodes the actual content to be transmitted. For each pair of tokens, say token I and J, the model computes the dot product of token I's query with token J's key. This dot product measures alignment, how much token I is looking for what token J has. These raw scores are scaled, divided by the square root of vector dimension to prevent the dot products from growing too large, and then passed through a softmax function that normalizes them into a probability distribution. The scores across all positions sum to 1. The result is an attention weight for each pair. How much token I attends to token J. The output for each token is the weighted sum of all value vectors, weighted by these attention scores. Token I's new representation is the blend of information from every other token, proportioned by relevance. The model runs this process multiple times in parallel, multi-head attention, typically 32 to 128 heads per layer. Each head has its own learned Q, K, and V matrices, so each head is free to learn a different kind of relationship. Researchers have found that heads that specialize in syntactic dependency, tracking subject-verb agreement across intervening clauses, semantic co-reference, linking it to its antecedent, positional patterns, attending to the previous token or to tokens at specific distances, and what are sometimes called induction heads, heads that detect and continue repeated patterns, implementing a kind of in-context pattern matching. The outputs of all heads are concatenated into a single vector and projected through another learned matrix back into the residual stream. After attention, each token's vector passes through a feed-forward network. two matrix multiplications with a nonlinear activation function between them. This is applied independently to each position. If attention is where tokens communicate, the feed-forward layers are where each token thinks individually, refining its representation based on the information gathered by attention. A single transformer block consists of one multi-head attention layer and one feed-forward layer, each wrapped in residual connection and layer normalization. The residual connection is architecturally simple but conceptually important. The output of each sublayer is added to its input. This means each layer computes a correction to the existing representation rather than replacing it. The residual stream flows through the entire model, and each layer contributes a delta, a refinement, and a further determination of what the input itself means. A frontier model stacks 80 to 120 of these blocks. The total forward pass, the complete computation from input tokens to output probability distribution, traverses all of these blocks in sequence. At the end, a final linear projection maps the last token's vector to a distribution over the vocabulary. I want to emphasize that sequential structure. The model's computational depth is fixed by its architecture. For any given input, the same number of layers process the data, performing the same number of sequential operations. The model cannot think harder about a difficult problem by running more layers. It has exactly as many steps of serial computation as it has transformer blocks. If a reasoning task requires more sequential steps than the model has layers, the model cannot complete the reasoning in a single forward pass. This constraint, the fixed depth of the forward pass, turns out to be critical for understanding what happens at the frontier, as I will describe shortly. I'm going to talk about this a little bit at the end, but something to note in the midst of the technical complexity here is that from a tech standpoint, the philosophy and theology that is articulated often to us in terms of how we should understand the models comes across in the same sort of complexity. And so having a translation layer between these two groups ends up being vital, and that's something I'm hoping I'm providing a little bit of input on today. For your purposes, this may be the most important section. The question of what kind of tool AI is depends heavily on what the model builds internally, what structures emerge in those billions of parameters. The first finding is that models develop geometric representations of meaning. Each token is positioned in a space of thousands of dimensions, and tokens with similar meanings cluster together. More remarkably, semantic relationships are encoded as directions in space. The example that Matthew Harvey Sanders used of the king to queen with the approximate parallel vector for man and woman, for example, being tied together there. The concept of gender is encoded as a direction, royalty as another direction, and those weren't programmed. They emerged from the pressure to predict text accurately. Modern interpretability research reveals far richer structure. Models develop linear representations of concepts like truth and falsehood, time, spatial position, sentiment, and formality, each encoded as a direction in the embedding space. Researchers at Anthropic and elsewhere have used sparse autoencoders to decompose the model's internal activations into interpretable features, discovering features that correspond to specific concepts. A feature for the Golden Gate Bridge, a feature for Python code, features that activate during deceptive reasoning, features that correlate with factual confidence. More striking still, these features are not isolated. They compose into circuits, identifiable subnetworks within the model that implement specific behaviors. Researchers have reverse engineered circuits for indirect object identification. Mary gave the book to John. The circuit identifies John as the indirect object. For modular arithmetic, for detecting whether a statement follows from prior context. These circuits span multiple layers, involve specific attention heads for passing information to specific neurons in feed-forward layers, and can be intervened upon, clamping or ablating individual components and observing the effect on the behavior. What does this mean concretely? Consider how a model represents a complex entity, say the city of Rome. In the model's internal state, Rome is not a single fixed vector. Its representation shifts as the context shifts. Rome in a sentence about geography activates different features than Rome in a sentence about church history or Rome in a sentence about cuisine. Yet across all these contexts, there is a core cluster of features that are consistently active, features encoding that this is a city, that it is in Italy, that it is ancient, that it has political and religious significance. The model has, through training, developed a representation that gathers diverse data about Rome into a unified internal structure that persists across contexts while emitting contextual modulation. In trying to wrap my head around this from a philosophical and theological standpoint, I came to Lonergan's concept of things, which is an unhelpful term common to Lonergan's naming of things, I will say. It provides a useful vocabulary, but perhaps also a useful warning. For Lonergan, a thing is a unity identity whole grasped in data. It is what you understand when you grasp that diverse experiences, seeing something from different angles and different lights and different contexts, are experiences of the same thing. The thing is not a single datum, but an intelligible unity that organizes the data. The act of grasping that unity is an insight, an act of intelligence in response to the question. The model's internal representation of Rome has some of the structural features of a Lonerganian thing. It is persistent, unified, context-sensitive, and supports inference, but it was not produced by an act of insight. No question drove its formation, no intelligence grasped that these diverse textual data belong together. Gradient descent adjusted parameters until the statistical co-recurrence patterns of Rome-related tokens were encoded efficiently, and the reason those tokens co-occur in the ways that they do is that human beings who wrote the training text had already understood Rome, had already grasped it as a thing. The model's representations is a statistical residue of human understanding, compressed into high-dimensional geometry. It inherits the structure of an insight without performing the act of it. The training process itself deserves a precise description. At each training step, the model encounters a specific datum, a sequence of tokens. The loss signal indicates the gap between the model's prediction and what actually occurred. The gradient attributes this gap across the model's parameters. The parameter updates adjust the model's internal representations to better capture whatever regularity the training example exhibited. Over billions of such steps, the model accumulates structure, regularities composed into representations, representations composed into circuits, and circuits composed into the complex internal architecture that supports the model's capabilities. Now, is this accumulation process a process of insight? I want to take Lonergan's account seriously rather than stretching it by analogy. For Lonergan, insight has an irreducible structure. First, a question. The inquiring intelligence wonders, asks quid sit, cur ita sit. The wondering is a prior to and conditions the understanding. Second, the act of understanding grasps the intelligible form in a sensible or imaginative presentation. It penetrates the data, grasping why the pattern obtains, not merely that it recurs. Third, insight pivots between data and concept. Before the insight, there's a manifold of presentations after a formulation. The insight is the active moment that makes the formulation possible. Gradient descent has none of the structure. There's no question driving the extraction. The system minimizes a loss function. It does not wonder about anything. There's no grasp of why. The model encodes that certain tokens co-occur in certain contexts, but it does not grasp the reason they do. And there is no phantasm being penetrated. The model processes vectors, not sensible presentations to an inquiring mind. What the model does have is the encoded products of human primary insight, stored as a statistical structure in high-dimensional space. The physicist's grasp of why displacement relates to volume is encoded in the patterns of the physics textbook. The jurist's grasp of why precedent constrains judgment is encoded in the patterns of the legal corpus. The model compresses these products into efficient statistical representations, and the representations are genuinely useful because they inherit the structure that human insight put into the text. But inheriting the structure of insight is not performing the act of insight. A library inherits the structure of everything its authors understood, but the library itself doesn't understand. The recombination, too, though, is generally productive. The model doesn't merely store the patterns that it has encountered, it generalizes. A model that has learned the pattern of English irregular verbs from examples can correctly inflect verbs it has never seen. A model that has learned the structure of logical arguments can follow valid inferences on novel premises. A model shown 3 examples of English to Latin translation in its prompt can translate a 4th despite never having been explicitly trained on that task. This capacity, called in-context learning, demonstrates that the model has extracted something more than just these particular associations. It's extracted some sort of transferable structure that recombines the products of human insight in novel configurations, and sometimes strikingly so. The thing is, though, but the novelty of the recombination should not be mistaken for novelty of understanding. Archimedes, stepping into the bath, grasped something that no one had grasped before, the reason the water rose. A model that produces a novel sentence about displacement and volume is recombining patterns that exist because Archimedes had already had that insight. The model's generalization operates by interpolation across the encoded products of human understanding. It recombines what humans have already understood in patterns consistent with what humans have already formulated. You can see as technologists, though, why we end up using a lot of human thinking analogous terms, because it's really hard to describe accurately the stuff that these models are able to do without relating them to the way in which it's recombined products of human understanding. In some ways, and this is where I think a lot of the thinking in this particular conference can go, is how do we articulate something that is close to our reasoning in this fashion without continuing kind of to refer to it as merely statistics, albeit very powerful ones over billions of parameters. Okay. Now the other side. If what I have described is correct, that the model stores and recombines the products of human insight without performing insight itself, then the absence I am about to describe should not surprise you, but it's worth naming. Lonergan's framework distinguishes the act of understanding from the act of judgment. Having grasped a possible intelligibility in the data, the knower asks, is it so? This question initiates a reflective process, marshalling evidence, checking whether the conditions for affirming the insight are met, and reaching a virtually unconditioned, a conditioned whose conditions are in fact fulfilled. Judgment, what Lonergan calls reflective insight or secondary insight, is the rational affirmation or denial that follows from this reflective grasp. Without it, one has a bright idea, but not knowledge. The model has no operation corresponding to this reflective act. This is not a matter of degree. It is not that the model judges poorly, it does not judge at all, in the sense I have just described. The model produces outputs, sequences of tokens with varying degrees of statistical confidence, but it has no internal process that evaluates whether its output is true as distinct from probable given the training distribution. It cannot distinguish between a pattern it can correctly identify and a pattern it has confabulated, generated because it is statistically plausible rather than because it is verified. Of course, the technical manifestation of this gap is a hallucination, the model's tendency to produce text that is fluent, confident, and wrong. A model might cite a non-existent paper with a plausibly sounding title and author. It might describe a historical event that never happened, or attribute a quotation to the wrong person. The linguistic markers of certainty are present. The output reads exactly like a confident assertion, but the confidence is statistical, not epistemic. The model has not checked. It cannot check because it has no mechanism for reflective verification. Let me make this technically precise. During inference, the generation of a response, the model performs a forward pass for each token. The forward pass is a fixed computation. The same layers, the same operations, the same depth. There is no branch in the architecture that corresponds to, am I sure about this? No layer checks the output of a previous layer against the external standard of truth. The model's internal representations include features that correlate with factual accuracy. Anthropic's interpretability work has found truthfulness directions in the embedding space. But these features are statistical artifacts of training, not instruments of reflective verification. They were learned because truthful text has different statistical properties than false text, not because the model has truth-seeking operation. This is the point at which the concept of things becomes illuminating from the other direction. Lonergan's thing is not merely a unified representation, it is a unity grasped by intelligence and affirmed in judgment. The model's internal representation of Rome was neither grasped nor affirmed. It was produced by parameter adjustments under prediction pressure, inheriting this structure from texts written by people who had both grasped and affirmed. The model has statistical unity without understanding and representation without judgment. The alignment techniques I described earlier, RLHF, constitutional AI, and others, partially address this gap, but in a revealing way. They do not give the model a capacity for reflective insight, of course. They train the model to produce outputs that a human judge would affirm. The judgment remains external. The model learns to predict what a human would judge to be correct, which is different operation from judging itself. Now, I want to bring you a little bit into the state of the art because two developments, one published in January and one being built now, and that could, 5 months from now, I could say the same thing, bear directly on what I've just described. First, reasoning models and the fixed depth constraint. Recall that the transformer's computational depth is fixed, the same number of sequential operations regardless of problem difficulty. In January, the a year ago, DeepSeek was launched, releasing a model called R1 that circumnavigated this constraint through chain of thought reasoning. Matthew talked about this a little bit. What's fascinating about chain of thought reasoning is that the model will generate intermediate tokens that externalize results into a context window where they become available for attention in subsequent forward passes. So what this enables is that each generated token buys an additional full traversal of the model's layers. The token stream functions as a scratch pad, an external working memory that extends the model's effective computational depth. In January of this year, some researchers published a paper called Reasoning Models Generate Societies of Thought. They asked what makes the scratch pad so effective. Is it simply more tokens? No, what matters is structure. The reasoning traces of effective models do not read like monologues. They read like conversations. Question and answer sequences, perspective shifts, conflicts and reconciliations, differentiated roles, functioning as skeptic, verifier, creative proposer, and synthesizer. Reasoning models exhibit these conversational behaviors at rates hundreds to thousands of percent higher than instruction-tuned models, even controlling for trace length. This causal direction was established through feature steering. Using sparse autoencoders, the researchers identified an internal feature associated with conversational surprise. Amplifying this feature approximately doubled accuracy on hard math benchmarks. The conversational structure produces the improved reasoning, not merely accompanies it. Under steering, the model engages genuinely different computational pathways, different attention heads, different expert subnetworks, and different feed-forward regions. Most striking, models trained with reinforcement learning that rewarded only correct answers spontaneously increased their use of conversational behaviors. Models fine-tuned with conversational scaffolding learned faster than those fine-tuned with monologue, and the benefit transferred across problem types. It's a fascinating kind of architectural shift that allows multiple conversations that gets around the layers problem of transformers initially. So that's a way of solving it from just a pure model standpoint. While academics kind of study those behaviors from a model standpoint, industry is already building systems that exploit them. At a conference last month, a speaker described their program for building autonomous digital workers. AI systems that are onboarded into an organization, taught how to do a job, and deployed into social settings with persistent identity. The architecture runs concurrent agents, social, task, initiative, heartbeat, reflection, atop an event bus system with hierarchical memory, procedural memory that distills successful tool call trajectories into reusable skills, episodic memory that abstracts interactions into learnings, and semantic memory that maintains per-person knowledge files. A heartbeat system wakes the agent at intervals to check commitments, groom memories, proactively reach out to people. An initiative agent catches promises the social agent made but failed to act on. The system produces a daily diary. The design philosophy is fascinating here. The agent's identity file is written as impressions, not prompts, designed to activate latent space rather than to provide instruction. The Maxim BA model maximist and an orchestration minimalist leverage everything the pre-training already encodes. Write as little scaffolding code as possible because the models will subsume it shortly. I describe this not to endorse it, but because it shows you the practical trajectory. These systems have progressed well beyond chatbots. They are systems designed to be colleagues, temporarily coherent, proactive, socially embedded. The philosophical questions here are very interesting, and the engineering specifications are already being implemented. We have teams at Microsoft, for example, who have agentic coworkers that, if you didn't know, are more or less indecipherable from human agents in the same context. Okay, so what to make of these kinds of new shifts? Chain of thought reasoning is a memory technique. The model compensates for fixed computational depth by serializing computation through token generation. If it were merely a memory technique, the format should not matter. However, the format does matter. Conversational scaffolding outperforms monologue scaffolding controlling for trace length. Now, why is that? A monologue scratchpad commits to an early path. Each token is conditioned on what precedes it, and the statistical pressure is towards coherence with what has already been written. Wrong initial approach in the monologue propagates this error, a mode collapse phenomenon. The conversational format disrupts this. Wait, but what if? Forces the attention mechanism to attend both to both the original reasoning and to the challenge. Different QK dot products, different value vectors, a representation distinct from what either perspective alone would produce. Broader search over the solution space. The technically precise summary is, of course, that the society of thought is a scratchpad organization strategy that induces diverse search by structuring external working memory in a dialectical rather than a linear format. Now, the relationship to insight and judgment. The dialectical scratchpad is the model's closest approach to something that looks like reflective verification. The skeptic re-examines premises. An observer might see something resembling the process Lonergan describes, checking whether the conditions for affirming an insight are fulfilled. But mechanistically, this is a recombination under a different search strategy, not judgment. The model skeptic generates tokens statistically associated with the pattern of skeptical inquiry as it appeared in training data. Data written by people who are actually skeptical, who actually did seek verification. The mechanism is search diversification, not truth-seeking. The improvement in accuracy is very real. The improvement in something deserving the name judgment is not established. The same thing applies to these digital workers. The initiative agent that catches a broken promise is not exercising responsibility. It is pattern matching on the textual structure of commitment and follow-through. The heartbeat system that grooms memories is not reflecting. It is executing a scheduled procedure. The system's temporal coherence is real and practically useful, but it is not self-knowledge. The deflationary account, of course, holds, but it leaves a kind of a residual question. Why is dialectical organization more effective than linear? The optimization theory answer, diverse search outperforms uniform search, is correct as a mechanism, but the convergence is striking. A machine optimized for nothing but correct answers discovers under accuracy pressure that the most effective structure for its reasoning is multi-perspective adversarial deliberation. The tradition represented in this room has practiced multi-perspective adversarial deliberation for centuries, and for the same reason, it finds truth that monologue misses. Whether this convergence is coincidental or reveals something about the structure of how these statistical models are obtaining generalization out of the underlying corpus is a very interesting question, not one that I can answer, but I note it for you. Okay, now let me draw some of these threads together in the direction of the conference's first question. What kind of tool is AI? Here's what the technical picture gives you. A large language model is a mathematical function that takes sequences of tokens and produces probability distributions over next tokens. Its hundreds of billions of learned parameters encode statistical structure extracted from a corpus of text written by human beings who have already understood the world, who have already had insights, made judgments, and formulated their understanding in language. The model compresses the products of that understanding into high-dimensional geometry, unified representations of entities, relations, and patterns that inherit the structure of human insight without performing the act. These representations support generalization, novel recombinations of familiar intelligibilities, with a productivity that goes well beyond memorization but falls short, of course, of understanding. The model does not possess insight in the sense that Lonergan describes. There is no question driving the extraction, no grasp of why the pattern obtains, no penetration of phantasm by intelligence. There is gradient descent, minimizing prediction error over the statistical residue of human thought. The result is precisely because human thought is structured, and that structure is preserved partially, approximately, in the statistical regularities of text. The model does not possess any operation corresponding to reflective insight, the act of verifying one's understanding is correct. It produces outputs without asking, is it so? It confabulates precisely because it has no mechanism for distinguishing a retrieved pattern from a generated one. The alignment techniques that shape its behavior are external impositions of judgment, not the internal exercises of it. Its most effective reasoning emerges when its computational scratchpad is organized dialectically, multi-perspective, adversarial, and conversational rather than linearly. This organization improves accuracy by diversifying search over the solution space, but the mechanism is search diversification, not reflective judgment. The model's closest approach to verification remains a strategy for improving the odds of encountering the correct recombination of encoding understanding, not a truth-seeking act. So what kind of tool is this? I would describe it as a tool that stores, retrieves, and recombines the products of human primary insight at unprecedented speeds and scale, while possessing neither the insight that produced those products, the reflective operation that converts understanding into knowledge, nor the deliberation that grounds responsible action. It is a system that operates on the encoded results of the first level of cognitional activity without any access to that activity itself. It manipulates the fruits of intelligence. It is not itself intelligent. I want to close by identifying what I think the technical picture most urgently needs from this room. The field of AI is moving at extraordinary speed. The capabilities I have described were, in important respects, impossible 5 years ago. The societies of thought finding I described is 2 months old. The architectural innovations that make these systems efficient enough to deploy globally are being published faster than any individual can track. What the field lacks, and what it is groping toward without the vocabulary to articulate, this is the silver lining I find in every AI conversation I have with my colleagues, is the question of what it means to be human comes up much more often than it has in my previous decades of existence. What the field lacks, and what it is groping towards without the vocabulary to articulate, is a precise account of what these systems do and do not do with respect to understanding. We as engineers speak of understanding, attention, reasoning, and alignment because these are the closest natural language terms we have for what the systems do. But the tradition represented in this room has spent centuries distinguishing the many things those words can mean and determine which of those meanings entail which others. I've used Lonergan's framework today, insight, things, reflective, insight, judgment, because it provides the most precise vocabulary I know for articulating what the technical picture shows. The technical reality I have laid out is not going to simplify. The systems will become more capable, the functional analogs will become more convincing. The pressure to treat them as the real thing or to dismiss them as mere tricks will intensify. What is needed is neither credulity nor dismissal, but precision. The kind of precision that can say exactly what is present in these systems and what is absent, and why that distinction matters. That is the work of the heuristic of generosity, from both the technical side and from philosophers and theologians. The technology is going to move forward. The tradition has the resources to answer it. I look forward to the Q&A and how we come to a better understanding of how to articulate these systems in the richness that we are developing them. Thank you.